Welcome to Pavinar's, Webinars for the Pavement Community. My name is Andrew Bram, and today I'm going to talk about a document that Dr. Shane Underwood and I put together titled Fatigue or Not Fatigue? That is the question. So this document was one of our fun side projects, and it's actually based on a much larger, more comprehensive document. And that larger, more comprehensive document was actually put together by 48 researchers in our community. And there's a link to this document titled State of the Art and Practice and Fatigue Cracking Evaluation of Asphalt Concrete Pavements below in the description. But I do want to make it very clear that the document that I'll be talking about today, the Fatigue or Not Fatigue document, that is based on a second, larger document that was put together by our colleagues. So the work that Dr. Underwood and I did here is based heavily on work done by our colleagues, and I cannot tell you how much we appreciate all of the work they did in putting together this much larger, more comprehensive document. So there is a link to this larger, more comprehensive document below in the description, and then there's also a link in the description for the Fatigue or Not Fatigue, that is the question document, which is free on ResearchGate. So why did Dr. Underwood and I put together Fatigue or Not Fatigue? That is the question. Well, it's because we were struggling to reach a consensus on characterizing fatigue cracking. Why were we struggling? It's because there's over 12 experimental methods and there's over 12 analysis techniques all dealing with fatigue cracking in the field of flexible pavements. That's a lot. And we know it's a lot because if you look at some other common distresses, such as low temperature cracking and rutting, there's only about 4 test methods for low temperature cracking, and there's only about 5 test methods for rutting. So compared to low temperature cracking and rutting, we have a lot of experimental methods and analysis techniques to quantify fatigue cracking. Now, why did this happen? Well, we believe that there's a gap in literature on the underlying perspectives and philosophy of fatigue cracking. We think that over the years, an implicit association has been developed between fatigue cracking and intermediate temperature cracking. And finally, third, we believe that there's a misunderstanding between the linkages of experiments and analysis for fatigue cracking. Now, there is quite a bit to unpack in those 3 whys. Now, there's a lot of fatigue tests out there, a lot of fatigue analysis techniques, and those whys are what started motivating us to dig deeper. And how did we begin to unpackage this sequence? Well, we went back in time. We went back to the 1950s where we believe the roots of fatigue are held, and that is in the Washoe and Ashto road tests. The Washoe and Ashto road tests led to classical fatigue theory in the 60s and 70s, led by Berkeley and Nottingham. All of that work in the 50s, 60s, and 70s really led to the road to SHRP, and that is because all that work in fatigue cracking led to rutting in our roads. After SHRP was implemented, we feel that there was a divergence of cracking tests in the 2000s and 2010, and now we're sitting here in step 5, in intermediate temperature cracking, and is a new direction going to go forward? Well, let's start with the roots of fatigue and let's work through this sequence. In the roots of fatigue, the Washoe road test took place in southern Idaho in the early 1950s. It involved 10 different cross sections, anywhere from 2 to 4 inches of asphalt and 2 to 18 inches of aggregate layers. They found that the 4-inch asphalt surface provided a far superior product, and the thicker sections limited deflections on the surface layer and retarded deterioration. So let's keep that third bullet in mind about thicker sections retarding deterioration. Around this time, Veeam in California started thinking about how deflection and cracking were related, and he started recommending structural design procedures that included fatigue and also some other factors, trying to understand how we can start to relate the deflection to cracking and how we can have better structural design procedures. Now, also around this time, we had the Ashto road test, which was in northern Illinois. This showed a shift from soil classification and soil tests to pavement layers. They looked at 3 to 6 inch thick asphalt sections, and they also found that the thicker hot mix asphalt pavements made for higher performing structural sections. So going back to the third bullet from Washto, thicker sections retarded deterioration. Again here, thicker sections made for higher performing structural sections. Now another big takeaway from AASHTO was it led to the equivalent single axle load, or an easel, and the importance of easels in pavements. They really ushered in the introduction to looking at what loads were being applied into pavement structural design, which was a very, very large step in our history of pavement structural design. So how can we start to move from these roots of fatigues to classical fatigue theory? Well, the University of California, Berkeley and the University of Nottingham saw that these test sections noticed that thicker sections were performing better, and so they found that repeated load or fatigue was a prevailing problem in the field, and they set about trying to solve that problem. This was lab focused, and what they did is they characterized asphalt materials under repeated load, but they also at the same time identified the need to evaluate the materials as part of a pavement structure. So from the get-go, they recognized that we had these material behaviors and we needed to link that to pavement structures. And they knew that we needed a thick enough pavement so the stresses in the pavement structure did not cause excessive deformation, which would lead to fatigue cracking. And what they did is they started the development of foundational fatigue equations, and they based it on Miner's hypothesis, which is where the number of cycles to failure, N sub F, equaled a constant, which is a material-specific constant, multiplied 1 divided by the strain, and that 1 divided by the strain was to another material-specific constant power. Now let's focus a little on this strain, this epsilon sub I. The I indicates load control, and you may also see that as epsilon sub T. So both epsilon sub I and epsilon sub T indicates load control. And you can replace that with an O, an epsilon sub O, which would indicate strain control. Now, stress versus strain, does this matter? In short, yes, it does, very much. And it stimulates a relevant question. Do pavements respond to tire loads like constant stress or constant strain? So as a tire goes over a pavement structure, is it constant stress or is it a constant strain? Well, according to Carl Montesmith, it's really neither. Real pavements are neither pure stress nor pure strain. And that is because stiffer pavements, either higher modulus or thicker layers, behave more like stress control, and softer pavements, lower modulus or thinner layers, behave more like strain control, and you have bending stresses. Based on that, we have a new component to the fatigue equation, and that's the max stiffness. And if you incorporate this max stiffness, or the mixed stiffness, into the fatigue equation, you simply multiply the mixed stiffness to the power of beta, and you get a new fatigue equation. And you can see here epsilon sub T, that T represents that we are in stress control. Now, this is from the AASHTO road test. A lot of work that was done by Kingham, Witzak, and Clayson led to the development of this mixed stiffness and also the new material term beta. And the constant in the fatigue methods are not from lab tests, but they're actually calibrated to field performance. And this is a very important distinction here. This means that we're taking the lab behavior and we are actually calibrating it through the material constants to field performance. Now, how does this relate to lab testing? Well, the test that kind of came out at the end of the day was the 4-point bending beam. And this has roots from Veeam in the 1950s, who we discussed before. It was refined by many, including Montesmith, in the early 1970s, but it continued being refined through the SHRP program. Now, there's been a lot of improvements in data acquisition and control system, but at the end of the day, AASHTO T321, which is the 4-point bending beam, that has the roots in Veeam and Monosmith. It's gone through a lot of iterations, it's gone through a lot of improvements, but AASHTO T321 is intimately connected with classical fatigue cracking. Now, there were other tests also being explored that never really gained as much traction. That included torsional tests, axial fatigue tests, diametric loading, and cantilever. But at the end of the day, the 4-point bending beam test is intimately connected with classical fatigue cracking. And the definition of classical fatigue cracking is you have cracks in the wheel paths. Those cracks begin at the bottom of the pavement structure and they propagate up. So this is all a summary of classical fatigue cracking. Now, unfortunately, this fatigue cracking work led to rutting in the 1980s. And in the 1980s, mixtures were becoming highly susceptible to rutting. And this was aided by AASHTO pavement design guides. So all this work was done on fatigue cracking, but inadvertently it started leading to rutting. And there are various reasons this started happening, including air voids, asphalt binder content, the lab compaction methods, increased tire pressure, axle loads, traffic volume. The list goes on and on, but much of the focus was on materials and material-related factors. And a very nice quote from the 50th AAPT annual meeting from Dr. Steve Brown, who is at Nottingham. He said that years ago it was cracking and lots of research on fatigue. That doesn't seem to be a problem now. What is happening presently is that rutting has emerged as a problem. And this is a direct quote taken out of the discussion section from an AAPT paper at the 50th AAPT annual meeting. There are many other quotes, there are many other papers that reflect what Dr. Brown said very succinctly. And these are the types of thoughts that led to SHRP. So SHRP is short for the Strategic Highway Research Program, Asphalt Research Program. SHRP is much easier to say. This is a 6-year program which was $112 million in 2023 US dollars. It included 8 major research projects and 15 supporting studies. There were 3 umbrella topics that included performance-based specification, asphalt binder characterization and evaluation, the testing and measuring of asphalt aggregate interactions and mixtures, and asphalt modification. And they wanted to get performance-based, readily implementable, and employ fundamental property tests that allowed for informed pavement design. So these were the 3 umbrella topics under that $112 million endeavor. The biggest outcomes at the end of the day were fundamental tests, an emphasis on aggregates, and the SuperPave gyratory compactor. So let's fast forward to the 2000s. Cracking again has become an issue. And this is where we start talking about the divergence of cracking tests. So the pre-1990s fatigue cracking tests, the data could be merged with outputs from a layered elastic analysis in pavement design. The 1990 crack tests have their roots in fracture mechanics and energy principles. And it was a shift from fatigue-specific cracking to general cracking. And Dr. Underwood and I believe that testing temperature is a big part of potential confusion here. That is because fatigue cracking and intermediate temperatures are closely related. This is just kind of an assumed relationship when we're going in the 50s, the 60s, and 70s. Fatigue cracking and intermediate temperatures are closely related. Other reasons were at high temperatures, the damage healed, so any sort of high temperature cracking, you really didn't see anything. If you did start thinking about high temperature cracking, you also start looking at low temperature cracking. If you combine those temperatures, it averages to those intermediate temperatures. And the mechanistic design methods use mean annual air temperature which are intermediate temperatures. So what's happening here is in the 1990s, we're thinking about cracking tests. We're thinking about intermediate temperatures. So we're really seeing as a shift from fatigue focus to intermediate temperature focus. Now let's take a look at what some current intermediate temperature cracking tests are. We have the 4-point bending test, which is empirical, energy, and constitutive. So you can see in the left-hand column here, we have experiments. In the right-hand column, we have analysis. Those are two key components. So the 4-point bending test, this is what was developed in the 60s and 70s. As we move forward, we have a supported bending and the loaded wheel tests. These are empirical and energy analysis based. We have cylindrical shape, we have indirect tension shape. That's empirical, energy, constitutive, and fracture based. We have trapezoidal tests, which is empirical and constitutive. We have overlay tests, which is empirical and fracture. And then a whole bunch of tests, dog bone, semicircular bend, 2-notch prisms, and a wedge notch test. Those are all fractured based. If you want to learn more about these tests, take a look at that longer document, because each one of these tests, each one of these analysis components has a section describing them, written by the people who actually developed them. So lots of good information in that longer document. But what Dr. Underwood and I tried to do was tried to collapse all of these experiments, all these analysis components into a smaller, easier to understand message. And we did that by breaking down the type of analysis. That was the first step. So if we look at continuum, this is a bulk material response, a stress or a strain, to number of repetitions to failure. Empirical uses continuum. This relies on experiments alone. It relies on fatigue laws, and it has a relatively high level of variability. Constituum is continuum based as well. This uses a damage theory or a damage function, but the models are key. There are many different continuum-based constitutive models, including damage, healing, thixotropy, heating, moisture-coupled, many more. Energy is also continuum. This is somewhere between empirical and constitutive. It uses the input and the number of cycles to failure and couples an underlying mechanism. But all three of these are continuum-based. They're bulk material responses. Compare that to fracture. These are measured at low temperature, and it can be linear and elastic. Now, fracture has since moved into elastic plastic, viscoelastic, non-linear, but at the end of the day, fracture is not a continuum. There's some sort of existing flaw, usually in mechanically inserted notch, but it doesn't matter at the end of the day what temperature it is. What you do need, though, is that stress concentration in order to get that fracture failure. And these experiments and analysis are from two underlying perspectives. So we have all those experiments, we have all these different types of analysis, and there's two different underlying perspectives, and that is, are we looking at a structural perspective or a material perspective? And these are different approaches to quantifying fatigue cracking. So structural factors include layer thickness and other properties. They have boundary conditions. The materials must accommodate but resist in order to perform. And we need to make sure we evaluate properties that feed into the structural design or life. This all has to do with the structural design focus. Now compare that to a fatigue or a materials design focus, and this is where you're less concerned about estimated fatigue life, but you're more focused on ranking. So is material A better than material B? It's more focused on accepting. Does material A pass some sort of minimum level, or do you reject that material? And really at the end of the day, you get an index value. And this is complicated, trying to think, what are we addressing? Are we addressing structural questions, or are we addressing material questions? How do we run a test in order to evaluate a structural issue? Do we just evaluate material issues? So these are very difficult questions, trying to look at the structure, the pavement structure, versus the materials that are within those pavement structures. And what this did is it led to our subway map. So those of you who have been to London and ridden on the tube, you should recognize this. It's very similar. And what we're trying to do here, this is really the cornerstone, the keystone of Dr. Underwood and I's fatigue or not fatigue paper. And this is the connections between the methods, the perspectives, and the analysis and the experiments. And there's a lot to talk about here. I just want to focus on two things. One, what are these stations? If it's a circle station, it's a performance test. If it's a square station, it's an index test. What are the color lines? The color lines are the test geometry. Is it a 4-point bend? Is it indirect tension? Is it a cylindrical shape? Those are all test geometry. Now, Dr. Underwood and I developed this in order to provide a foundation for our community to move forward. Now, we have some initial thoughts, but we want this to be a foundation for our community to move forward. So, what are some of our musing? So, all of these test methods were developed continuously in the same general sequence. Someone notices a pavement is failing by intermediate temperature cracking. They develop a mechanical test that is repeatable and it distinguishes between the materials. They generalize that test to other standard materials and they establish a ranking procedure for materials. We feel that this is a specific sequence that every test method should go through in order to establish credibility. Now, we also believe that these tests focus several questions. So based on these tests, based on these musings, what are some questions that Dr. Underwood and I developed? Well, the first is, are index tests beneficial? Are tests that simply rank material that are isolated from structural modeling beneficial? Are there correct material damage growth viewpoints? So, is it important to think about crack initiation? Is it important to think about crack propagation? Do we need to think about both of them? How does this material damage and how does the damage spread? And then where can simplifications be made? Now, this is a very important question, and that's because the final choice of a test may be based on cost and ease of use, not on the ability to meet a measure. So there's a lot of things to unpack here. We feel that all of these tests need to be developed through this 4-step process, but we also believe that these tests need to go through some questions about what they're trying to capture and how they're going about it. Then, at the end of the day, when a test is proposed, what is the motivation behind that test being proposed? So let's take a look at this recap. We went through the roots of fatigue. We went through classical fatigue theory. We talked about how fatigue led to rutting. We talked about a divergence of cracking tests. And we feel that we need to go in a new direction. So the new direction, why is there so many tests? We personally, Dr. Underwood and I, believe that there is a missing link between structural design tests and material tests. We believe that today, fatigue tests are inherently linked to intermediate temperature testing. We believe that these two terms are too often used simply interchangeably, yet they're very, very different concepts. We believe that there are links between the different test methods and the analysis techniques. We believe those links are ambiguous and complicated. We think that moving forward, that we need to be very careful when we're talking about cracking, We hear a lot of talk, I have used it, about the pendulum analogy. We had too much cracking in the 60s, the pendulum was on the left. In the 80s, we had too much rutting, the pendulum was on the right. Now in the 2010s, 2020s, we have too much cracking, the pendulum's back on the left. We need to be very careful with that because the cracking in the late 2010s may not be that classic fatigue cracking from the 60s and 70s. Therefore, talking about a pendulum, again, implicitly starts tying fatigue cracking to intermediate temperature cracking, which we believe is a dangerous assumption. So fatigue cracking does not necessarily equate to intermediate temperature cracking. Lots to think about here. Again, we're academics. We provided a foundation for moving forward. We're not here to supply all the answers necessarily. We think that this is an incredibly complicated problem, but we want to try and provide a foundation to move forward. But we do have some parting thoughts. We believe that there are three gaps in fatigue cracking in today's thought process. We feel that newer tests are on islands, and there's little or no framework to build bridges between these islands. And the same can be said for analysis techniques. We believe that a lot of our mindsets are based on traditional testing and traditional analysis, and that could cloud our judgment as we're developing these newer tests. And we think there are misunderstandings when trying to link our newer tests and analysis together. So we have over 12 different tests, we have over 12 different analysis techniques. We think that there are understandings when trying to link those all together. We're certainly not in the 60s anymore. The cracking of today is not the cracking of pre-SHRP. We also believe that the 60s cracking tests, for example, the bending beam, had a robust foundation. And that foundation has to do a lot with tying it to structural design. If you recall, when we were talking about Monosmith and Brown, when we were talking about Nottingham and Berkeley, from step one, they were talking about how do we tie this to structural design. We feel that that's not happening. We're doing a lot of material tests now, and we're not tying it to structural design. And because of that, our newer tests are lacking such a solid foundation. And that includes the tests that Dr. Underwood and I work on. We both dealt a lot with cracking. We are not immune to this. We believe, though, that we need to be part of a solution moving forward. Now, again, there's no specific answers, but we hope that this white paper is a basis for building a solid foundation moving forward for newer tests. So thank you very much for joining us today. Again, please view the full documents in the links down in the description. We hope you follow up on it, and we hope that this can be used for moving forward.